We move on to the next speaker, Mandar Deshmukh. Mandar will talk about charge transport across tunable superlattice barriers in graphene. Mandar, 30 plus.
Okay, it's a tough act to follow after Ami's talk, but nevertheless I will summon the courage to give a talk after that. It was pretty amazing stuff. So today I'm going to talk about some experiments that we have been doing which are fairly recent on tunable superlattices in graphene, and I'll give you a flavor of the understanding that we have and what things. I'll also point out what we don't understand. So needless to say, I'm fortunate to have very good students who do all the tough work, and I come and give talks. So Sudeepta, who's here, did all the experiments, and there were several students who contributed to it and from the group. These are the three theorists we have been talking to understand the physics of these superlattices in graphene. So this is my brief outline. I'll just, mostly for the students, I'll try to outline what are superlattices, why bother with a superlattice of graphene. I mean, that's a question I ask myself whenever I do something new. What has been done so far, and there has been some things that have been done, and I'll try to specially point out what we have done different, and I'll tell you how we do these experiments. I'll show you the results, then make sense of all of it, combine it with what we have theoretical calculations, and what doesn't make sense, and then I'll kind of briefly summarize things. Okay, so that's the outline. So superlattices are very common. And you have any long-range periodicity in your system, this is very common in a lot of different aspects of solid-state physics, but certainly in transport, you can make superlattices in semiconductor heterostructures. And there's a very nice set of experiments and work that was earlier done at IBM where you can make very nice devices using superlattices. So this is the earlier paper of Isaki and Su at IBM. And technology and growers just take it to a whole another level. And these are superlattices in essentially what I would call top-down heterostructures, where you have periods of these are very closely spaced. The atomic fringes are right here, so you have essentially a very, very long-range periodicity in the system. You can also have superlattices of bottom-up nanostructures. So these chemists are really incredible, and I really love them. They take colloidal crystals and they put them together and make superlattices of not just one kind of colloid, but many different kinds of colloids. Okay, so these are basically the superlattices, and they can lead to very interesting physics. Okay, and this is the broadest definition of the superlattice, the kind that the graphene zoo is very rich. There are lots of creatures which have different kinds of heads, and so one kind of superlattices that people have been making is with alternating layers of graphene, boron nitride, whatever else you can peel off, and you stick it between these things. So this is an example of the hierarchy. So you have boron nitride, graphene, and you can just keep on stacking them, and you get superlattices. But these are through the plane of graphene, for example, and that's something that I want to distinguish from the kind of devices that I will be talking about. Okay, so these kind of measurements people have been doing, and there are lots more coming through. What I'll be talking about, I want to distinguish a little bit with superlattices which are lateral. So in the plane of graphene, there is some interesting physics that is accessible. So one kind of experiments that have already been done is, you exfoliate, peel off graphene, and you put it on a substrate which is crystalline, and there is interaction with the substrate, and it essentially imprints some part of the potential on graphene, and you essentially get some sort of a beating pattern. So this is experiments done by this group way back in 2009, where you have iridium 111 surface and you put graphene on top, and you look at what you're seeing here these are not atomic fringes, but these are Moiré patterns, and you go ahead and look at the ARPES data, and you will see kind of mini additional Dirac cones. The band structure essentially gets modified, and you will see mini bands form in graphene. So that's the kind of experiment that has been done. Also experiments with boron nitride have been done as well, where people see that boron nitride is really not the happy substrate that everybody wants it to be, but it really interacts with graphene and interacts with graphene. So these are experiments done in Brian Leroy's group at Arizona State, where they do STM measurements on boron nitride on graphene, and they see kind of Moiré patterns, and then they go ahead and do spectroscopy, and they see in the density of states features which are akin to additional essentially additional Dirac peaks, and I'll be talking more about it in the next couple of minutes. Okay, so certainly it's an interesting system to not just with graphene, but monolayer graphene, but bilayer graphene, and potentially with topological insulators where you can engineer the band structure at some level. Okay, so it has the potential to interesting physics, and the energy scale set by this superlattice potential is inversely proportional to the spacing. So the smaller, the tighter the spacing that you get, you have a much larger energy scale associated with that periodicity. Okay, so let me just repeat a little bit of what you said. We want to make lateral superlattice of graphene. We want to do band engineering. We want to look at collimation of electrons, and I'll tell you where all of these kind of things come together. And these are actually things happen at the same time. So just to give an example, people have done theoretical calculations. This is Louis group at Berkeley, which has done very nice calculations showing that you have superlattices of graphene, and these are just essentially, if you don't have a superlattice, you get essentially the wave function of the electrons, and this is when you have a superlattice, you get kind of incredible collimation. This is just theoretical work, so it has potential to electron optics. There are interesting aspects of introducing another energy scale in the quantum Hall physics, and although we have lots of data, we have no understanding, so I'm not going to be talking about. There are aspects of optics which can be quite fascinating as well. Okay, so the question to ask is, okay, so superlattices have been done many times. What is it that graphene has something to offer, some interesting physics? And the key ingredient that is different is this, something that people have studied quite a bit recently, is Klein tunneling. So just for the students, if you make a barrier in graphene, and you look at, kind of shoot Dirac particles on one side of the barrier, and you look at the transmission on the other side, it's actually, you will get perfect transmission at certain angles as long as the superlattice potential is abrupt. And perpendicular to the barrier, you get perfect transmission. So that's really kind of unusual, and if you want to look at Kronig Penney kind of picture, you have to kind of take into account the different boundary conditions, but it nevertheless works out. Okay, so in cases of smoothened potential, things change just a little bit, and you can get a very nice kind of collimation just even with a single barrier. So the key ingredients is you're looking at a Kronig Penney kind of picture, but you're looking at Dirac physics. That's the thing that is different, and you can use those conditions to look at, you can essentially theoretically solve the problem with certain assumptions. Okay, so how have we realized it? So we use combination of gates. So we have, we don't use boron nitride. We have silicon oxide on silicon. Okay, and we have graphene. We have aluminum oxide on top, and which is ALD grown dielectric, and then we have a lot of finger gates on top. So these periods can be up to 40 to 50. This is a little bit tricky to do, and it has been figured out, electron beam lithography. So these are the finger gates, and this is the flake of graphene. And if you look in, these finger gates are very fine. These are 27 nanometer lines of metal, and the total period of the superlattice is about 150 nanometers. Okay, so that's really the device. And so we have two gates, bottom gate, top gate, and we are going to use a combination of these to apply voltages and essentially create regions of electrons holes sitting right next to each other, separated by roughly about a smoothness of something like 20 nanometers. Okay, all right. So so the challenges in this particular thing are just to make narrow gates, and the other technical challenges you want to make very thin dielectric, primarily because the smoothness of the potential is essentially set by the thickness of the dielectric. So the thicker the dielectric you make, this field is going to spread out. It's just the sort of spreading of the electric field. Nothing. So you really want to make something very thin, but at the same time, its integrity should be very good as long as you apply large voltages to it. Okay, so that's really the device. So what we want to realize is this cartoon picture. We want to have a repeating structure. I will show we have a repeating structure where on one region I have, let's say, just the one gate acting, on another one I have another gate, and I will counteract the effect of one gate and essentially dope the graphene in a totally different set of charge carriers by applying a combination of voltages. Okay, and this is the height of the barrier. The height of the barrier can be calculated just by asking yourself the question, how many charge carriers are induced in graphene either by just the backgate, or in this region which has the top gate and the backgate both acting, you can find out what is the net algebraic sum of the carriers that are induced in this region, and you basically ask, how high does the bucket, kind of a conical bucket, fill up as I induce these carriers? And the difference in these two kind of charge neutrality points gives me the height of the potential. Okay, so it looks kind of a little bit complex, but this is basically what I just told you. You induce carriers from just the backgate, and then in the regions combined with backgate and topgate, and the difference of it gives you the height of the potential. So now let me tell you a little bit the smoothness of the potential. We have done reasonably detailed FEM calculations recently, where the smoothness of the potential is about 20 nanometers, so it's not really abrupt. The width of the top gate region, because of the smoothing of the electric field, when its graphene sees this potential, is roughly about 75 nanometers or 70 nanometers. So you have regions of 75 nanometers and 75 nanometers, which are alternating with respect to each other, and the total period is about 150 nanometers. Okay, so what do we experimentally measure? We measure zero bias. Most of our measurements are zero bias, although we have done a fair bit of sort of DC bias measurements as well. So we do zero bias measurements at 300 millikelvin, and then I will show you data that these whatever signatures we see persist all the way up to 100 Kelvin. And this is sort of what you see as a combination of backgate and topgate. So let me just orient you, and the color scale is the measured resistance. So all of this data is raw data, and let me orient you a little bit. So this quadrant here of the parameter space, this has backgate positive and topgate positive. So that basically means with both the gates, I'm inducing electrons in graphene, and with varying density, but nevertheless same sign charge carriers. Whereas exactly said, a symmetric side is in this quadrant, I have essentially the same physics happening, but not with electrons, but with holes. Okay, so I have holes, but of varying density. Okay, now if you look at this particular two quadrants, they are fairly symmetric, and these are the regions where it's possible to have alternating regions of p-n junction. Not everywhere, but some regions you will have alternating regions of p-n junction, because you want the backgate or the top gate to counteract the effect of the backgate, and that doesn't happen at all points of this quadrant. Okay, and what you notice here is that you will see kind of streaming out conductance or resistance peaks, which kind of fade in and out, sort of disappear, then suddenly they split up into two, and as you follow it along, they split up one by one as you go along sort of roughly the diagonal of the measurement space. Okay, and essentially the same symmetric thing happens when you go in the opposite direction as well. So the fact that you have symmetry is a comforting aspect of the measurements. Okay, so if you take a slice right here at the charge neutrality point of the whole system, and you see a very nice Dirac peak, and if you take a slice right here, you see very nice oscillations. This is just raw measured resistance. There's no derivative involved. Okay. So once you have this, naturally you start to think, what is going on? Why are these resistance oscillations there in these measurements? And so just to kind of fill you in on what people have seen before, this is a little bit older data and people have cleaner data. But this is if you just have one single top gate, you have essentially a PNP or NPN kind of junction. So the parameter spaces still look similar. This is earlier work from Philip Kim's group. But you see kind of large peak and a small peak, which is because of the charge neutrality of the region, which is covered by both the top gate and the back gate. So the back gate and the top gate, for a narrow strip, they compete with each other to induce carriers, and at certain point in a linear combination you will get a charge neutrality point. So but here nevertheless you don't really see any kind of complex sort of resistance oscillations, and that's something different about our measurements. And it should be because. So do you see anisotropic resistance in this sense along the? Yeah, so we have done measurements. Right under the superlattice, doing both kind of measurements is a little bit tricky because of the electrodes that you need to get in and everything. So we have some measurements, and I can talk to you more about it. Okay, so So just to remind you again, this is sort of the thing that sets the potential, and we can extract out these numbers and try to kind of look in terms of what is the height of potential when we see these kind of resistance oscillations. So what the physics is that we set up a potential barrier, and in the region where we have large barriers, we certainly see oscillations, but we don't see oscillations everywhere. Okay, so I'll come to the physics of it. So what do we see if we look at very close, sort of this is, we measure data much finer. So you clearly see these kind of one quadrant, you see these resistance traces come out, then they kind of split, and it's kind of just increases by one after certain intervals of the parameter space. So just a kind of quick idea about the relevant parameters for the device. Typically the device, I mean, these are in the days of boron nitride and suspended graphene, these are relatively low mobility, but they have interesting physics. So the mean free path is roughly about 80 to 100 nanometers. So we are not quite in the ballistic limit. We are sort of in the diffusive. Yeah. We have about 50. I think Sudipta can tell you 40 to 50 or 30, depending on the device. Okay. And the phase coherence length we extract from a part of the flake which is still covered by aluminum oxide but does not have the top gates. We can extract out, and the coherence length is about 600 nanometers. Okay, so that's a decent fraction of the device, and the Fermi wavelength, just for people who are interested, it varies with the density, but it's roughly of the order of tens of nanometer. So one energy scale that is introduced in the problem is the superlattice energy, and this is something that I will energy scale that I will talk about, and it's very key to understanding the physics of what's going on. And this is the superlattice energy, and it's referred to by different people different ways. But this is the energy scale set by the length scale of this periodicity. And in our case, we would like it to be narrower, but this is about 5 MeV. And the other relevant energy scale is the puddle energy scale, which is about 70 to 80 MeV. So it's still a pretty large dominant energy scale, and as I will tell you later on, a bug becomes a kind of feature of the experiment when I'll return to this aspect of the puddle.
How does it compare to maximum Fermi energy?
Yeah, so you will see so you're leading me on towards our experiment. So we can apply potentials which are much larger than that, and we see different physics, and when we apply potentials comparable or smaller than the puddle energy scale, we don't see that physics. Okay, so that's a kind of cross-check in the experiment. So
Fill up the puddles and make it.
yeah, at least we can make the potential barriers much higher than the puddles, and that. And so there are these features I already pointed out. At low density, we don't really see any oscillations, but at large densities, we see oscillations. And certainly here, we don't really see, although there are potential barriers here, but they're much smaller. We don't see it. Okay. So one way to understand the nature of these resistance oscillations is to ask, how do these respond to other kind of perturbations to the system? And one of them is magnetic field. So if you look at these, it's not really showing up very clearly here, but you have these fringes right here. And as you apply a magnetic field perpendicular to it, they kind of move as a function of magnetic field. So if I'm sitting as a slice right here, as a function of magnetic field, they get a peak falls on a throw, so it's exactly a phase shift. So this physics, in some sense, is understood from the perspective of Klein tunneling, where you have and a lot of theorists have done work on it. You have a single barrier, and you have a kind of a P-N-P junction. And as you look at the transmission of problem, in the presence of magnetic field, in the absence of magnetic field, you pick up additional phase, and that does indeed is expected to have a phase shift. So the resistance peak should move as a function of energy, and that's really what we see. So in some sense, this is a confirmation that what we are seeing is the Klein tunneling combined with the magnetic field and the superlattice is giving rise to these resistance oscillations. So the other important parameter that we have is we can actually vary the temperature and ask what happens to these features, and that will give us a better understanding. So if we just vary the temperature continuously at roughly about 1 Kelvin slice, this takes about something like 15-16 hours, and you can see that these resistance oscillations start from around 300 millikelvin. They don't really change all the way up to 4 Kelvin, and then essentially smear out somewhere close to 100 Kelvin. But they're fairly robust. If you want to take slices, they look like this. So at low temperatures, they're pretty robust, but they're really not gone even very close to 100. Okay, and if you look at the sort of visibility of these oscillations, they're dropping down as a function of temperature. It's really hard to fit anything in because it's a relatively small temperature range. So one, again, cross-check is that the temperature scale which at it vanishes roughly, at least for our measurement case, is about 100 Kelvin. And if you extract an energy scale associated with it, which is about something like 8 MeV, and this is in the very close neighborhood of our superlattice energy scale, which is the energy scale set by this periodic superlattice that we have within the system. So it is again expected that if our thermal energy becomes larger than this length scale, all these, if the physics is associated with the superlattice, it should kind of go away, and that kind of makes sense as well. Okay, so there are two cross checks that I've already given you. One is is the magnetic field, which combines with the Klein tunneling and it matches predictions. The other is this temperature. So next I start kind of thinking about what's going on. So if I just plot in Mathematica the height of the superlattice potential using that equation that I showed you, but I plot it as in units of the superlattice energy, and I plot it as a contour plot, and I will see these constant, constant potential contours. So this is, just to tell you, this is giving me a contour plot of calculated height of the potential as a ratio of the superlattice energy scale. Okay, so I can clearly see that I get very large barrier heights in the regions where I have charge carriers of opposite sign in this region and this region, as I had kind of qualitatively indicated to you. These numbers I will come back to a little bit later, but there are some multiples of 4 pi, and I will explain that a little bit at least. But as you see here, in this region, the potential barrier is very high, and here it's not so high. Okay. Now this is my experimental data. To make sense of it, I don't, because both the gates affect the height of the potential barrier, the V naught. I want to take slices of this data at constant potential barrier to make sense of the theory and calculations. So what I will do is I will put these contours on this data and extract out data along the contour. So that will give me essentially resistance measurements along constant potential. So if I wanted to do, I could experimentally as well write up a LabVIEW code and which does a combination of it, but essentially it turns out to be the same. So if I take slice right here, which is at a very small potential height, this is about 6 pi in times 5 MeV, I don't really see any resistance oscillations. Okay. And this is 26 pi, and I will come back to this 26 pi business in a little bit later. You see very nice oscillations, and that's basically sort of one aspect of the physics that connects to the other energy scale in the system, which is the puddle energy scale. Okay, so the role of charged puddles. Okay, I'm sorry, but there's a very important set of references related to which I've got cut. But the role of charged puddles is very key to graphene, and this is something unusual about graphene that makes the physics interesting. So if I want to look at, these are again slices of the same data, but these are contours of as increasing potential as you go higher and higher in this direction. Okay, so if I take slices at u equals 2 pi, so 2 pi, this is in units of 5 MeV, so you can multiply it by 5 MeV to get the. If I increase the potential, I see that there is modification as I keep on increasing the potential height. I will see oscillations come in, but at low potential barriers, I will not see any oscillations in my system. Okay, and so I kind of already gave away the story. When the puddle energy scale is much smaller than the potential barriers that I have imprinted on graphene, I see very nice resistance oscillations. Otherwise, I don't really see. And this kind of, in a qualitative sense. Is it like filling up of the mini bands? Sorry? Is it filling up of the mini bands in the Fermi level? Yeah. I will kind of show that a little bit. So if this is the cartoon picture, if my puddles are like this and I'm trying to imprint a potential which is comparable to it, it's really kind of not. It's basically no good. But if I have puddles kind of on my graphene which are of a much smaller energy scale, then I can imprint the potential much more kind of effectively. Okay, so now I quickly, how much time do I have?
You have 12 more minutes.
Okay, great. I should be just in time. So let me just go a little bit. Now comes the part where I try to make connection with what understanding that people have. So I will basically go into follow theoretical approaches. So people have been kind of predicting different things with superlattices of graphene because it is an area of interest for a variety of reasons, and people have, in some sense, already explored it. So there have been lots of papers. I think, in some sense, Louis group at Berkeley was one of the first to get started in this, and they have many papers. And The approach that we'll be following in this explanation is basically by these guys, but their approaches and predictions are nearly similar.
5 more minutes actually, 17 minutes rather than 12.
How much do I have effectively?
I said 12 minutes, now it's 17 minutes.
Okay, so I have more time. Okay, okay. So all right. So okay. So that's good. So you have so these guys all start with, most of them at least start with a square potential. Okay, because that's really a tractable problem to handle. And there are some interesting things happen that vary with as a function of duty cycle. So you have a barrier height which is varying, but nevertheless the qualitative features remain the same. So what do you do? So you basically solve this problem, essentially a Kronig Penney model for the Dirac electrons. You match the boundary conditions and you use a transfer matrix approach, which is details are in this paper. This is not our work. Net result is you want a dispersion relation of the charge carriers in the presence of these, and it gets significantly modified. It has these very complex looking equation which you can solve numerically to get the dispersion relation as a function of potential. So you have kx, ky, x is the direction perpendicular to the barriers, ky is the direction parallel to the barriers, and you can solve this dispersion relation numerically to extract meaningful quantities and to do calculations for conductance, which I will show you in a minute. So this is where the physics, always the competition of the potential or the intrinsic energy scale is this energy scale which I already explained to you is a superlattice energy scale. And when things increase in multiples of it, you see the band structure actually getting modified. So what's really the key, it's this dispersion relation. And one thing that I will point out to is, which is quite different from what we do experimentally, is that our potential is certainly not square. Okay, so we'll have to correct our picture, and I'll come to that in a couple of slides. Okay, so what is new in these kind of superlattices is as the potential that you crank in with your knob, you sort of have a competition set up between the energy scales of the problem, and you can tune the band structure of graphene, monolayer graphene continuously. You can do similar things with bilayer graphene as well. And what really happens is this. So if you just follow this plot, this I set up a 4 pi times whatever is the height of the potential. I get a dispersion closed for kx equal to 0. I get ky. So this is just at the cusp of forming one more Dirac peak, okay, and it will become clear in a minute. Then I go to 6 pi, I crank up the potential a little bit. I get, I believe I get this black dashed and dotted line. I get additional peak in my band structure. Very close to it, I can think of linear dispersion all over again. I keep on cranking, I get another, and I go beyond 8 pi. So in multiples of 4 pi, new Dirac peaks kind of pop in. And I go to 10 pi, and still one will come into the picture. So what's really happening is, depending on how you want to think about it, as you crank the height of this potential, you are bringing in essentially some sort of mini bands are forming within the system, and the transport is, needless to say, sensitive to what's happening. So another way to look at it is you can kind of plot the dispersion relation. So as long as the duty cycle of this potential is 50-50, the Dirac peaks the additional Dirac peaks will emerge right at the same energy of the original Dirac peak. Otherwise, they may go up and down depending on the details of the duty cycle. But you will see additional peaks showing up as you increase the height of the potential. So this is really what our system is. So let me just plug that back, and V0 is the quantity that I already gave away. It's what we get control from is the gate voltages. So we have essentially, as far as graphene is concerned, we treat it as the energy scale associated with the lattice of graphene is much larger. We don't really worry about it. It's smooth. Then the next energy scale is the puddles. So that's really the difference. As I said, there's just besides the fact that you kind of tune the band structure, the exciting physics is that you can, if you look at around these additional Dirac peaks, if you look at the velocities, so crazy things happen to velocities in these superlattices. They get renormalized, the Dirac cones become squished, but what is neat is that each of these additional periods of 4 pi, there is near complete collimation that happens for the electrons that are traveling through the system. So Vx is in red, and Vy, which is parallel to the barriers, is in blue. So Vy basically goes to 0 at every point, at every instance, a new Dirac peak is emerging in the system. Yeah.
So that means it propagates very freely along the edge.
No, Vy is so if these are my barriers, Vy is this, and Vx is perpendicular to the barriers.
So which velocity goes to 0?
Vy. So along perpendicular to the barrier, the electrons essentially get collimated. Yeah, Arindam.
Yeah, but did you think it on any kind of potential scattering? I know your V3 path is long.
Yeah, so the calculation I will show is within the diffusive limit, and it works out fine. You will see. So we don't have to use ballistic transport. Yeah.
So one more related question. So are you saying that the mobility essentially just sets, given a particular array dimension, the mobility just sets the scale to a gate voltage? Is that all it is?
No, I didn't understand that.
Like given a certain mobility, suppose I increase the mobility, I would be able to see all this at this lower gate voltage, and nothing else really changes.
In some strange way, maybe we can talk more later, but in some strange way, maybe that is correct, but I need to understand your question a little bit more better. So there is exciting physics happening, just not the fact that you're tuning the band structure, but you also get kind of collimation. So as of now, our current set of devices don't really have very interesting means to measure collimation, but that's something that we are kind of thinking about. So you can actually match this up reasonably well with calculation. So you can, within a kind of a diffusive transport, which is sort of the limit in which we are in, you can calculate the conductance along perpendicular to the barriers, and that's something that we have done following these guys. For our potential barriers are much higher than what they have actually calculated for. And you can see these oscillations as a function of Fermi energy, which is also what we see. These are just offset for clarity. So every time the potential is increased by units of 4 pi, there's an additional peak that pops into the conductance, very similar to what we have in our experimental data. We have also done, because our duty cycle is not really 100% clear to us, so we also have done calculations for duty cycles other than 50-50 of the potential, and we see qualitatively it's the same results. Even if our duty cycle is different of the potential, it's not going to change the fundamental basic physics that we see. Okay, so I'm almost done. So now it's time to compare our calculations. So we can sort of like, we can plot the whole plots that we have instead of VG, VBG, and VTG. We can plot it as Fermi energy and V0, and we can look at the slices of the data. And what we see is, if we take a slice, we certainly see oscillations, and we can calculate the period. So the period is roughly about 20 MeV in our measurements. And if we look at the calculations, the period is, sorry, I was cramped for space. The period here is smaller. Remember again, these are square potential barriers that we have used for the calculation. So the period here turns out, in experiments, turn out to be larger than what is predicted by theory. So it's time to kind of put everything together and say what matches, what doesn't. And so one part that kind of right off the bat, if I just compare the calculations, these things don't match. So we went back and we kind of looked at this thing a little bit in greater detail. So if you have a potential profile which is different from a square potential, if you have, let's say, a cos of kx kind of potential, the emergence of Dirac points happens under different conditions. So if you have a potential which looks like this, the condition for additional Dirac peaks popping out is basically some zeros of the Bessel function, J0. And what sets the period of the oscillations is this quantity, and in the case of square potential, this is basically 2 times 2 pi. In the case of smoothened potential, cos of kx is 3.1 times 2 pi. So if you have a kind of, our potential is neither of these things, but if it's smoother, you will basically get a variation in the period, so it makes sense experimentally. What we don't have quantitative understanding of is, if you look at, and this is something that Sankar Dasama pointed out when I was having a discussion with him, that the duty cycle, or rather the amplitude of the oscillations that we have in conductance here in the calculations is much larger than what we see in experiments. It's quite nice that we don't really have to take any derivatives or anything, but it's still smaller. And it could be due to disorder, and that's something that at this point we don't really have complete handle over it, but that's something that we want to kind of look at a little bit later. So just one slide to put it all together. So what we're really seeing is you have a potential barrier, and the strength of the height of the potential barrier is the largest in this region, as expected. And only when it crosses this puddle energy scale, and you look at, you will start seeing oscillations. And that's really sort of the take-home message of the experiment, and it kind of puts a bug, which is the kind of the puddle part is really a bug, and if we want, if we would like to have a control over it, and as of now we don't. So we have a cross-check within the experiment. So there are lots of neat things that can be done with superlattices and including optics. So this is sort of what I kind of advertised, and I think I should be able to put a check mark against all of this. So that's really my summary. Thank you for your attention.
Thank you. There's enough time for lots of questions. Yes.
Yeah.
Experimental question. So you are exfoliating on Al2O3, is it?
No, exfoliating on SiO2 and then doing ALD growth of thin aluminum oxide. So that's a little bit tricky to grow a very good quality. I mean, if you can do with boron nitride, I think it should work. I mean, the physics should not change, but we have used aluminum oxide. It's a little bit tricky to make on graphene, but it's been done.
Next, and then
If I understood right, if you so you are seeing this resistance oscillation because you are actually filling up various mini bands. So after a while, when you run out of all these 50 mini bands because of your 50 lattice phase, this oscillation should die away.
No, it's not the counting of the. I mean, it's not like that every period gives you a new mini band. It's basically the collective superlattice gives you mini bands, and depending on the strength of the potential. So it's not like we can count essentially a mini band associated with every period.
Shankar?
Yeah, let me just make a comment on disorder. I guess you know that the original Klein tunneling measurement in Philip Kim's group, Andrea Young's work, and actually Andre Geim had some data also, I think in nanoliters, that the resonance structures are very vaguely connected with Klein tunneling. Jens Berdersen and Enrico Rossi with me did a very big calculation of disorder where they included the self-consistently calculated graphene electronic structure using density functional theory, and they did a huge Landauer-Butiker calculation of Klein tunneling in that electronic structure.
Oh, okay.
It's a calculation that I did not think could be done, but they collaborated. One is at Berkeley, one is in Virginia, and those results then kind of reproduce that huge reduction, because Klein tunneling, it gives order 1 effect, and they see. They plot these things, you have to look at the ordinate. They plot this thing, they're not even seeing a 1% effect.
Yeah.
So I would think, based on that experience of mine, that in your experiment, disorder is also very important.
Yeah.
And so, the fact that things don't quite work out, if things worked out, I'd be very concerned, because you have a lot of disorder. Second comment is that this amplitude, can you go back to the amplitude discrepancy that you showed in the next to the last slide, alluded to my comment. I just wanted to make the comment crisper.
Okay.
Yeah. So let's say that you do this theory, and I thought that you had that theory in the presence of finite temperature. You can do this theoretical calculation.
Yes, it's in the presence of.
All you need to do is just convolute it.
That's right.
Right? So what I would suggest you do a finite temperature calculation with an arbitrary temperature, not your actual experimental temperature. Make the temperature a free parameter.
Okay. And
then fit that and see what the amplitude agrees. Then whatever temperature you get, I predict that will be higher than the temperature that you need at the real temperature, and the difference in the dingle will be the dingle temperature, which will be connected with disorder.
So can you repeat? Can you repeat that?
You do this calculation at some finite temperature to get fit.
Yeah.
You get a temperature, let's say that's 500 Kelvin, or 400 Kelvin, or 100 Kelvin, which will be much higher than the temperature. It's not going to be the real temperature.
Right.
Okay. That extra temperature that you are getting is the effect of disorder.
Okay.
It's
a measure.
technically called a dingle temperature, quote unquote. What I mean? And that I think will work.
Okay.
And that's what I would suggest you do. That will be a cheap and easy way, because this big calculation is very hard to do.
Yeah. Thank you. Jim had.
So one of the things that I'm not that I don't understand is that the oscillations that you see only occur when you have N and P, both. Yeah. But if I go into other quadrants of the picture, I still have a periodic potential, and it could be very strong.